Most people think World War II bunkers were about concrete thickness and steel doors, but the real fight underground was for breathable air. Thousands of civilians and soldiers didn't die from bombs or bullets. They suffocated. Smoke, carbon dioxide, blast pressure and oxygen starvation killed faster than shrapnel. Yet, in the middle of that chaos, engineers quietly solved the problem with a deceptively simple air system that required no electricity, no fans, and no moving parts that could fail under attack. It kept people alive for hours or even days after explosions sealed exits, and remarkably, the same principle still outperforms many modern survival shelters today. This wasn't advanced technology. It was applied physics, smart airflow control, and an understanding of pressure that modern survival gear often ignores. The problem World War II bunkers faced when the bombs actually hit. When high explosives detonated near a bunker, the danger didn't stop once the walls held. Shock waves forced superheated air and toxic gases through any opening. Fires outside consumed oxygen and replaced it with smoke and carbon monoxide. Inside, dozens or hundreds of people exhaled carbon dioxide into sealed rooms. Mechanical fans failed instantly when power went out or debris damaged motors. A bunker without airflow became a concrete coffin. German, British and Soviet engineers all reached the same conclusion early in the war. Any shelter that relied on powered ventilation would eventually fail. Air had to move on its own. The World War II bunker air hack relied on pressure, height and resistance instead of machines. The life-saving trick was passive overpressure ventilation. Bunkers were built with 2 or more air shafts at different heights, often with one intake near ground level and an exhaust rising higher through protected channels. Warm air inside naturally rose and exited through the higher shaft, creating a slight negative pressure that pulled fresh air inward. This chimney effect worked continuously, even when the bunker was sealed. Engineers added blast valves made from heavy steel plates or, weighted flaps that slammed shut under sudden pressure spikes, preventing shock waves from entering, then reopened automatically once pressure normalized. No switches, no motors. Gravity and physics did all the work. Filtration mattered just as much as airflow in keeping people alive. Fresh air alone wasn't enough when cities burned above ground. Many bunkers routed incoming air through long, narrow channels lined with charcoal, sand or layered brick. These materials cooled hot gases, trapped particulates, and reduced toxic compounds before air reached occupants. Some German Luftschutz bunkers even used moisture traps to condense steam and smoke, preventing lung damage during prolonged stays. The system slowed airflow deliberately. Slower air meant better filtration and less pressure shock. This balance between resistance and circulation is why these systems kept working when modern high-flow solutions would fail. The system survived direct hits because it expected damage. What made this hack superior was its acceptance of failure as inevitable. Engineers assumed parts of the structure would crack, clog, or partially collapse. Instead of fighting that, they designed redundancy. Multiple intake paths, oversized shafts, and simple valves meant partial damage didn't stop airflow entirely. Even a crushed vent could leak enough oxygen to sustain life. Modern survival shelters often fail here by depending on tight seals and precise tolerances. WWII bunkers survived because they leaked in controlled, intentional ways. The same principles quietly outperform modern survival tech today. Many modern bunkers rely on electric air scrubbers, HEPA filters, or sealed oxygen systems that work perfectly until they don't. Once power fails or filters clog, the system collapses. The WWII pompo etiquetos minibus itis potens chamatas codica deneses non underdans or the cursin then ansonderdems. You know, anyone building an off-grid shelter, storm room or emergency safe room can really apply the same logic today. By creating 2 airflow paths at different heights, lining intake channels with dense natural materials, and installing simple gravity-based backdraft dampers, you can actually maintain breathable air indefinitely, even without electricity. Applying this knowledge today doesn't require a bunker or any special tools, honestly. A practical example is just a basement-safe room. If you install a low wall vent leading outside and a higher exhaust vent routed through masonry or a metal pipe, natural convection begins right away. Adding a bit of length and a few bends to the intake path will improve filtration. And, filling a removable section with activated charcoal or even layered gravel and cloth does a pretty good job of mimicking those wartime filters. A simple weighted flap or metal plate is all it takes to prevent sudden pressure reversal during storms or explosions. This setup works silently, constantly, and doesn't really need much maintenance beyond the occasional cleaning. So, why was this wartime air hack quietly abandoned after the war? Well, after the Second World War, cheap electricity and mechanical systems, they started to replace passive design. Buildings became much more airtight and, honestly, quite dependent on powered HVAC systems. Those old bunker methods, really, they were seen as outdated rather than resilient. But, history shows that systems designed for worst-case conditions often outlast those optimized for convenience. Wartime engineers didn't care about comfort, honestly. They cared about survival when everything else failed. The real lesson modern survivalists and builders should take seriously is this. Air is the first survival resource, even before food and water. The World War II bunker air hack? Well, it succeeded because it respected physics, accepted failure, and worked continuously without supervision. It didn't need innovation, not at all. It needed understanding. That's why it saved lives then, and still it beats much of today's survival technology now. If you value forgotten engineering that actually works under pressure, this is knowledge worth preserving. So, subscribe to the channel for more deep dives into real historical survival systems. Share this video with anyone serious about preparedness and help keep these life-saving lessons alive.